Why?
Because it stops.
How do you know that? Doesn't say it in the problem, I don't think. Or does it?
No, it doesn't say that.
You're right, but why from the problem can we infer that it stops?
It just says until it reaches the spring.
Okay. There were two things sort of at the same time. My brain. All right, Isabella, say it again.
It just says it's sliding until it reaches the spring. So I don't know. I guess I just assume it's capped.
Okay, and it is a correct assumption. Anyone else about why from the wording of the problem do we know that it stops? Luis?
Is it because it basically says that it compressed the spring, but it doesn't say that it decompressed. Is that a word?
Oh, yeah.
So like, I'm assuming it stops once it compresses. It just stays there compressing on the spring.
And so okay, almost there. So what's the key word in there which tells you that we want it at the point when it stops?
Maximum.
That's the key word there. Maximum compression. If it's still moving, it's not compressed all the way. But I guess still moving to the right. It's not compressed all the way. So at maximum compression, that is the point when it stops. All right, so that's 0. And so now we are left with just the amount of kinetic energy we had to begin with is equal to the amount of elastic potential energy at the end. All this energy gets transferred from one form to another. So how much energy do we start with? Well, that becomes a plug and chug. So 1/2 times 31 kilograms times my initial speed, 15 meters per second squared. What does that equal to? Somewhere around 3,300. 3,400
87.5.
units. This is kinetic. I did plug into 1/2 mv squared. I'm finding kinetic energy.
Would it be K?
Or Newton meters?
Joules?
Newton meter would work, and joules requires less writing.
Okay. So, was it safe for me to think that, because I know you said maximum was the key word, but was it safe for me to think that the reason why we would cancel out that one is because the same with the ball problem, we throw it up and it has to come back down, so that was the stopping point?
Oh, the fact that if it does turn around, there has to be a stopping point at some point.
So,
Yeah, so I guess going along with that thinking. Yeah, as it compresses, I think most people have taken a spring, pushed it in, or pulled it out, and then bounces back. So yeah, given enough time, it would turn around, so it would have to stop.
okay. But I was thinking about the word maximum.
Yep. So maximum is just a different way of saying the point at which it would stop. Because the spring has a certain length, something hits it, it's going to keep compressing until it doesn't compress anymore. In other words, it stops.
All right.
All right, so I start out with almost 3,500 joules of energy. As it hits the spring, it gets transferred. So we're going to go for the hand gesture demonstration here. So we start out with all this kinetic energy and absolutely no potential energy. As the spring compresses, because it's this conservative work being done, it gets transferred from one form to another. So as it compresses, kinetic energy drops, the potential energy increases until there's no kinetic left. It's all potential. Potential energy is in this form. So that's got to be equal to 1/2 times K, which is a spring constant, times delta X squared. delta x. 12.794.
Will you explain what you just did again, please?
Here?
Yeah, I don't get why it's equal to the 3487.
Oh, why it's equal to this?
Yes.
Why that is equal to this, or this is equal to that?
Why that one's equal to that one.
All right. I start out with all this kinetic energy. We're working under the assumption that energy is conserved here, primarily because the only thing doing any work is a conservative force. So we have all this energy, and it's just going to get transferred from one form to another. So we start out with all this kinetic, it hits the spring, and then that kinetic starts dropping because it's going to slow down. Well, that energy has to go somewhere. That energy goes into the potential energy of the spring. And so we're taking all that energy and just transferring it all into potential energy. So the potential energy is that.
Okay, so we're just setting that equal to that second half of that equation?
And so we're setting the kinetic energy it starts with equal to the potential energy at the end.
Okay, I was just curious for like the rest of the equation with, that's why I was kind of confused.
Oh, these?
Yeah.
Well, this is 0 because the spring is just sitting there.
Okay.
And that's 0 because it stops at the end.
So the whole equation's 0.
The whole term. That whole term. Because V is 0, the whole term is 0.
Okay.
Because delta x is 0 initially, this whole term is 0.
Okay, so how do we get 12.79?
I did that in my head. We have this is equal to that. The math problem we're working with here is 3,487.5 equals 1/2 of 20, 10 x squared. That's the math problem we're working with. So we need to get to x, so first we have to divide by 10. And so I get 348.75 is equals x squared. And now we have to get to x. So we have to undo that, so we square root both sides.
Wait, what did you divide by 10?
I did. That's,
Oh, sorry.
I moved the decimal point. You're getting something completely different?
Hold on, let me just check real quick.
Oh, I realized my mistake. It's not 12.
I was gonna say it was
That's
18 something.
I don't know where that came from. It would be
18.67.
0.67?
Yeah, meters.
Okay.
And the 10x squared came from the half 20 NM?
Yes.
Okay, okay.
If you'd rather, you could have multiplied by 2 and then divided by 20.
Okay.
Yes, Kimberly.
So you have to do that because of the spring? Or you, like in each equation, whenever you get that, you have to solve another equation to actually get the answer?
In all the conservation of energy problems, you start out with a certain amount of energy, and something happens to it. The energy, this is the idea of energy is conserved, it goes somewhere. So if only conservative forces are doing any work, so weight, gravitational force, spring force, electric force, these are conservative forces. If those are the only things doing any work, it just gets changed from one form to another, from kinetic to potential or potential to kinetic. If non-conservative forces are doing it, you're transferring the energy from that object to a different object. So, ask your question again, please. I think I somehow got off track.
Like since you're giving the kinetic energy to the potential energy, whenever it's equations like that, you have to solve that first to get your actual answer in another equation?
Oh, solve the kinetic energy first?
Yeah.
Suddenly, exceptions pop into my head. The first problem we did was we had the box sliding up the hill. I didn't have to actually solve for the kinetic energy first in that situation.
Okay.
Just because mass canceled out mathematically, there was a simpler method.
Yeah.
But I could have solved for the kinetic energy first, and then set that equal to the potential energy at the end.
But it matters sometimes what you start off with.
Yes.
Okay.
Other questions on this problem? Other questions?
I'm sorry, I wasn't paying attention. I don't know if anybody asked this, but will there be like a question where it reaches its maximum length? Like if you stretch it out, would it be the same kind of equation?
Right. If I took this and I said we have this mass that comes along, hits the spring, compresses, and then in some freak of nature, the mass now becomes attached to the spring.
Okay.
And so now the mass is shooting out. How far will it stretch past equilibrium? Then the answer would be 18.67 meters also.
Also, everybody the same thing.
It would be the exact same answer. Because how far it compresses has a certain amount of energy, then that gets transferred into kinetic and then back into potential. And basically it doesn't matter if delta x is positive or negative because we're squaring it. So you end up with the same answer. Unless there's friction, but
Wait.
I would not subject you to that in this work.
So,
For a spring and friction problem.
so like compressed is 18.67, and then it becomes like what you just said, and it goes the other direction. Is it still gonna be positive 18.67?
Depends on the wording of the question. If I said how far does it stretch past equilibrium, then yes, there'd still be 18.67. If I said what is the final displacement, then suddenly we're into the, well, one of them's positive, one of them's negative.
Okay, okay.
But you wouldn't do that to us, right?
I have not done that in the past. But I could do it if you wanted me to.
No, thank you.
All right, just asking. Other questions? Brittany?
This is on a different question.
Okay.
Number 8, it's asking about loss of kinetic energy and the change. So we would just be subtracting the total kinetic.
All right, wait, hold on, just a second. Let me,
Okay.
head towards each other. Box A is they give you mass, initial velocity. I give box B's mass, initial velocity. They collide. And apparently perfectly inelastic collision because the two boxes have the exact same final velocity. Okay.
What's your question?
So would we just find out the total initial kinetic energy and before and after, and then the final kinetic energy total, and just subtract the after from the before to find how much was lost? We're just kind of like we did with momentum, but with the kinetic.
Yes,
energy.
absolutely.
Okay.
That would be the total amount of energy lost in the system. Let's see the question, how much energy was lost? What you just said, that's how you do part A. Part B, what's the change in kinetic energy for box B? You would do something very similar, except just look at the kinetic energy of B beforehand and B afterwards. And then C, how much work did A exert on B? Recognize that what A is doing to B is a normal force, because they collide, which is a non-conservative force. So non-conservative work is being done here, and that work being done on B would be equal to its change in energy. Box starts at rest 30 meters above the surface of Mars. Its dropped speed after it falls 20 meters. Okay. Notice in this problem, I didn't give you the mass. If that bothers you, make one up. If the mass is irrelevant for this problem, and if you need, so I would recommend if you're making up a mass, make it something simple like 1 kilogram.
Just doesn't mass cancel itself out in that problem?
It does, which is why I don't need to give it to you. But some people are not comfortable with that. They'll see the M in the problem and they'll go, you didn't give it to us. And that's fine, just make one up. If I didn't give it to you, either I made a mistake or it's not needed. On a test, you can usually tell by my response of, okay, how about, and then I make up a number. If that's calm or relaxed, probably you don't need it. If I go, oh, that probably I made a mistake. And this is version of this. Version 3, that's something if I'd been missing, probably would have picked up by now. So it's going to drop 20 meters. Is it actually hitting the surface?
No.
Okay. So we're starting here. It's going to drop 20 meters. I'll use new numbers here. 15 seems to be what I've been working with a lot. So 15 meters. We'll go ahead and keep it on Mars. And it starts at rest. And how fast is it going after it's fallen? 15 meters. And for those who just want the visual image, why don't we put this 40 meters above the surface of the planet? So how much kinetic energy does this thing have at the beginning of the problem?
0.
Why?
Because it's at rest. It's in the potential state to fall. I don't know.
What was the first thing you said?
Because it has potential.
Right, well, it's something that have potential and kinetic at the same time.
Oh, okay, so, but it's at rest?
Yes, that's the key right there. You all know the formula, you've recited it. There's the formula for kinetic energy. If V is 0, kinetic energy is 0. All right, so it has no kinetic. Now the question is, does it have any potential?
Yes.
Okay. What is the formula for the potential energy that we're going to use in this problem?
Which one?
Would it
The
be
one for this problem.
Would it be MGH?
It would be. Why would it be? Oh, Amina, question?
Wait, I'm confused. The 15 and the 40, which one would come first on this problem?
So a box starts 40 meters above the surface of Mars and it's dropped. What's the speed after it falls? 15 meters. All right, so we established there's no kinetic. Before we talked, we had, I think somebody answered it. I literally got distracted. Wow, that came out wrong. I apologize. What is the force acting on this when you drop it?
Acceleration due to
So work on the language.
Gravitational force.
There we go. Or weight or force due to gravity. I heard gravity by itself and then I heard acceleration due to gravity. So the force is the weight. Conservative or non-conservative? So what's conserved? That's right. All right, so we have energy being conserved as this thing falls. It has no kinetic to start with. To figure out if there's the potential energy formula associated with weight. I think somebody said it already, but we'll say it again. What's the potential energy associated with weight?
MGH.
Wow, that was not expecting unison, but there was a nice chorus there. All right, so there's my potential energy formula. M, I didn't give it to you, so it'll go away at some point. G is for Mars, 3.7 meters per second.
3.72. 3.71.
That'll fit in the short-term memory. All right, and H. What is the initial height?
40 meters.
Why?
That's how high it is off the ground.
That's not the reason why.
It's a start point.
Starts at rest.
It does start at rest, but that doesn't mean that the initial height is 40. We can,
It's being,
I have no problem with the initial height being 40 meters, then just, I want us to understand why isn't 40 meters.
it's being dropped from that height. Being dropped from that height.
Not the reason.
Okay.
Or that would be the reason that someone might pick 40 meters. That's not the reason why 40 meters is the initial height for my formula here.
Is it where it stopped at before hitting the ground? Right?
It's how far it would fall eventually, given our understanding of nature. If I dropped it, it would go 40 meters and then hit the ground.
Oh.
Wait, but you're wanting the H for the formula, not the height for the actual start.
That's correct.
Oh, okay, well, it's 15 meters because it's starting at 40 to whatever the stop point is 15 meters, the distance, the displacement.
All right, so why?
Because you said that.
Oh. Why would so you're saying the initial height is 15?
No.
You're saying
it's
the
40,
initial-
and then the ending is whatever 40 minus 15 is.
So 25.
Yes.
All right, let's do it that way. Let's go ahead and then we'll get back to what I was trying to get towards. All right, so I start out with absolutely no kinetic. It's all potential. Now, doing it what I had over there, I can just write down the same stuff. Initial energy equals final energy. This is initial kinetic plus initial potential is equal to final kinetic plus final potential. Who doesn't love more equations? This is 0 because the initial speed is 0. Neither of these are 0 the way we're approaching this. All right, so I've got mgh initial is equal to 1/2 mv initial squared